let's talk about improper integrals here for a few minutes. An improper integral is any definite integral that has some type of infinite behavior within the limits of integration. That infinite behavior could be a horizontal asymptote. Sometimes the limit is actually approaching infinity. Sometimes the infinite behavior is a vertical asymptote somewhere between the two limits of integration. So a few examples of integrals that would be considered improper. This first one is the most obvious kind, because looking at this, there is clearly an infinity for the limit of integration, so that's talking about end behavior or horizontal asymptotes in this case. So that one would be improper. The other two are a little more hidden because on the surface they look like normal antiderivatives. However, if you're paying very close attention to the functions, which you should always do, the function 1 over x, if you were to graph that, it has a vertical asymptote at x equals 0. And 0 is one of the limits of integration. So this would be an improper integral. This one also is a little bit hidden. The function 1 over x minus 2, if you were to graph that, you would see a vertical asymptote at x equals 2. So we have a vertical asymptote at x equals 2. And again, that vertical asymptote is between the two limits of integration. Therefore, both of these are improper integrals, even though they do look like a normal antiderivative that you would solve using regular integration techniques. So the way we solve an improper integral, when you identify the improper behavior, the infinite behavior, first thing we do is convert the antiderivative into a limit, because you are not allowed to treat infinity as a real number, and the way we do that in calculus is we use a limit to express it. So I'm going to say, let's take this antiderivative, and my improper behavior is occurring up here on the upper limit, so I'm going to replace that upper limit with an a, and I'm going to say, let's see what happens to this area as a goes towards infinity, and my function is 1 over x cubed, which is easier to integrate as x to the negative 3. Then once you convert the limit, the integral to a limit, you then solve the antiderivative like you would if there were real numbers for limits of integration. So to save a little bit of time, I did that real quick while the video was paused, or recording was paused. So once I do that, I now need to plug in my limits of integration. So that's going to be negative 1 over 2a squared minus negative 1 over 2 times 1 squared, which is 2. So minus negative is plus. So once I do that, now we go back and visit the limit, and I'll know what happens as a approaches infinity. So I'm going to go here and see what happens to this function, 1 over 2a squared plus 1 over 2. And as a approaches infinity, 1 over infinity approaches 0, and 0 plus 1/2 is 1/2. So there's our answer. Let's look at another one. This one is one of those that's not quite as obvious because the limits of integration are real numbers. However, always pay attention to domain. We have two issues here. One, we are dividing by 0, which is a problem. And the natural log of x by itself has a vertical asymptote at 0 as well. So we have both the numerator and denominator indicating improper behavior or infinite behavior. So I'm first going to turn this into a limit. So let's turn this into the limit. And in this problem, my improper behavior is happening at 0, so I'll put a in the place of the 0 to 4 of ln x over x. And we're going to do this limit as a approaches 0. But before I go on, I'm going to make one little tweak to this limit. If I'm going from 0 to 4, I'm really interested in the right side of 0. So I'm going to go 0 from the right, and then we will work this antiderivative out, ignoring the limit until the very last step. So we're going to work this antiderivative out, and then we'll come back and revisit the limit. If you need practice with limits, you may want to, with antiderivatives, you may want to pause the video while I'm working this, because in about 2 seconds the answer is going to show up. And so if you want to pause it and work it out yourself, now's the time to do that. Alright, so there we go. This was a U substitution problem, and you can kind of see my thought process here on paper. U is natural log x, 1 over x dx is the du, so it turns into a very nice integral after the U substitution, and you end up with natural log x squared over 2 for the antiderivative, and evaluated from a to 4. We're down here, and this is where we revisit the limit, and I'm interested in knowing what happens to this function down here as a approaches 0 from the right. So as a is approaching 0, well, the natural log of 4 squared over 2 is a big ugly number, so that's not going to go anywhere. That's just going to be unaffected by the behavior at a, or at 0. Then minus, here I have the natural log of 0, and if you remember the graph of natural log x, this is one of those limits, it's easier to think graphically. Natural log x looks something like this, and as we approach 0 from the right, that guy is going down towards negative infinity, so that'll be negative infinity squared over 2, which ends up being natural log of 4 squared over 2 minus infinity. And this case is different than the first problem we did. The first problem, when we solved it, we ended up getting a finite area. In this case, the integral from 0 to 4 gives me an answer of negative infinity, meaning this is not a finite area, obviously. So when you get a case like that, the word we use for situations like this when the area is not finite is we say that this improper integral diverges, or you could say is divergent. So if you get a finite answer, then you could say that the area converges to 1/2. And if you get an infinite answer, a non-finite answer, then the answer is the integral diverges. So I want to look at one more, and that's this one. And this one, again, if you're not paying attention, you may not recognize the improper behavior. And this is a sneaky problem, because if you don't recognize this as an improper integral, you could actually work this out and think you get the right answer, because no errors will present itself in your work. And here I'm going to show you what I mean. Alright, so here what I did is I worked out the antiderivative, ignoring the fact that there's a vertical asymptote at 0, and the antiderivative of 1 over x squared is negative 1 over x, and if you evaluate it and do the arithmetic, you'll get an answer, a wrong answer, but you'll get an answer of negative 1. However, that's not correct, because you need to recognize any domain issues, and in this case we do have a vertical asymptote at x equals 0, which renders all of this work wrong. So you need to pay attention to your functions and make sure that there is no infinite behavior between the two limits of integration. Yep. So now what I'm going to do is go to the next page, and we'll look at this thing and see how it works out as an improper integral. And the first thing I'm going to do on this one's a little bit different, because my improper behavior, my infinite behavior, is happening at 0, which is between the two limits of integration. So the first thing we're going to do, in this case, what I'm going to do first is rewrite the antiderivative so that the infinite behavior is one of the limits of integration. So in this case, I'm going to split it into the antiderivative from 0 to 2 plus the antiderivative, from negative 2 to 0 plus the antiderivative from 0 to 2. Then once you get it set up with two integrals, now we actually have two improper integrals, and we have the option of doing it this way. I could solve this one as a limit, so I'd say let's do the limit as a approaches, and my infinite behavior is at 0, and from negative 2 to 0, that's the left side of 0, so negative 2 to a of 1 over x squared. And then we would add to that the answer we get when we do this improper integral, which would be the limit as a approaches 0 from the right this time of a to 2 of 1 over x squared. And we could work out both of those antiderivatives and add their two answers to see what the actual answer is to the whole thing. Now, there is another saving grace to this problem that doesn't always happen, because I would say more often than not, you will have to work problems like this out as two separate improper integrals. However, if you're paying close attention to the function, if you're paying really close attention to the function, you may notice that 1 over x squared is an even function, so whatever is on the left side of the y-axis will mirror whatever is on the right side of the y-axis, which means my area from negative 2 to 0 is going to be the exact same as the area from 0 to 2. So instead of doing all of this, I'm going to take this original function, this original limit, antiderivative, and I'm going to rewrite it as twice the area from 0 to 2 of 1 over x squared, which I then would convert to a limit. I'm going to keep that 2 all the way out here, so 2 times the limit as a approaches 0 from the left of the antiderivative from 0 to 2, a to 2 of 1 over x squared. And now I'm about to work out that antiderivative. So if you want to try it yourself, pause the video because my answer is going to be up here in about 2 seconds. All right, so there is our antiderivative evaluated from a to 2. Now we're going to go back to the limit and we're going to see what happens to this function. So minus a negative is plus. We're going to go back to this function, see what happens as a approaches 0 from the right. And what we're going to run into here is we have negative 1/2, which is unaffected by a, plus, and 1 over 0, that should be from the right, I'm sorry. That's the right side of 0. So 1 over 0 from the right, that's going to be positive infinity, and negative 1/2 plus infinity is infinity, which means this thing, what's wrong with my D? Whatever. This thing diverges. So it actually turns out that this is a divergent integral. However, if you work it out incorrectly, you will get a finite answer of -1, and it looks right, but it's not right because you didn't notice the vertical asymptote. So anytime you have a fraction, you should always, 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 always be aware of any vertical asymptotes, any discontinuities, something along those lines that would make your problem a little bit wonky.